start with the eclipse. So once again, if we have the sun, and if here's the moon, and if the earth gets in the way of the sun and the moon, and the earth's shadow is cast on the moon, that's going to be a lunar eclipse. And in this case, no matter if it's a partial eclipse or a full eclipse, that shadow cast is always going to be curved. And so the only shape that can make a shadow, no matter the angle, which is a curve, is going to be a spherical shape. So we already knew back then in 600 BC that the world was a sphere. And by looking at the arc of the shadow relative to the size of the moon, we knew that the differential size between the Earth and the moon was like 4-to-1. Then this was the other slide I didn't show you that I just talked about for 10 minutes. This is the image that Aristophanes had. So here's Syene. And again, here's the distance from Syene to Alexandria. And the angle between Alexandria and Syene is about 7 degrees. And that comes from the fact that on June 21st, the sunlight striking straight down with no shadow cast on Syene, which is about 23.5 degrees north latitude. And at that same time and day in Alexandria, the shadows of actually 7 degrees. And that 7 degrees is due to the curvature of the Earth. And so distance from Alexandria to Syene divided by 7.2 degrees equals the circumference of the Earth. So circumference of Earth divided by 360 degrees. So it's just a simple ratio. And if we solve this ratio for circumference of the Earth, CE equals 360 times the distance of Alexandria to Syene over 7.2 degrees. This was the equation that Aristophanes used, and it was really, really close to what the actual value is. Now we know that the circumference along the equator is about 24,000 miles because the radius of the Earth at the equator is about 4,000 miles. And I'm using the term at the equator because the fact of the matter is the Earth is not a perfect sphere. It's a little bit squished. And so the distance at the circumference is larger than it would be otherwise if we were just talking about a perfect sphere. But that's how they did it. Quite clever, as a matter of fact. Okay. So now let's go back and let's talk about some basic stuff. And again, this will be basic stuff for a lot of you. It'll be a review for some of you, and for some of you, it might be brand new. But the fact of the matter is we live on a big sphere relative to us. We're talking about the Earth, again, having a circumference of about 24,000 miles at the equator. And if you're doing any form of navigation on the planet, the question becomes, how do you find your position on the planet? Well, there's a variety of ways to represent planet Earth, and we're going to concentrate on one called the geographic grid. And in the geographic grid, we're dividing the world into north and south and into east and west. And what I want to do is just chat a little bit about it. So, for example, how do we know that right here the North Pole is at 90 degrees? How do we know the equator is at 0 degrees? How do we know that this is 30 degrees of north latitude and this is 60 and this is 30 degrees south latitude and that's 60 degrees south latitude, and so on and so forth? So let's come up with how they did this, and then the next step is, how do you figure out what your latitude is? And then honestly, how do you figure out what your longitude is? So again, latitude is north and south. Longitude is going to be east and west. How do they do it? Where do they come up with these numbers? So let's take a look at a very quick example, and let's talk about 45 degrees north latitude. If we were to draw the Earth, and this is like remarkable for me, that's almost a perfect circle. If I'm drawing the Earth here, and here's the equator, all the equator is doing is dividing the world into two equal hemispheres, the northern hemisphere and of course the southern hemisphere. And because this dividing line is the equal part between the two, we're going to call it the equator. And we're just going to define the equator at being 0 degrees of latitude. It doesn't have a north or south because it's not north and south. It's just 0 degrees. Now, if I put a dot here on the very top of the Earth, and if I draw an imaginary line that goes to the center of the planet, and this imaginary line extends to the edge of the Earth, I've just created an angle. And that angle is going to be 90 degrees. Therefore, this point directly on top of the Earth is 90 degrees north latitude. It's the North Pole. I can do the exact same thing in the southern hemisphere. So here's the South Pole. And the South Pole is going to be at 90 degrees south latitude because, again, it makes an angle of 90 degrees relative to the equator. So all latitude is where are you located relative to the equator. 45 degrees means that you're making an angle of 45 degrees relative to the equator. And so this would be 45 degrees north latitude. Here in the southern hemisphere, again, you can go 45 degrees, but this would be 45 degrees south of the equator, so this is now 45 degrees south latitude, and so on and so forth. Now, the fact of the matter is there's not just one spot on the Earth, which is 45 degrees north. There's not just one spot on the Earth, which is 45 degrees south. The fact of the matter is this is an angle of 45 degrees. This is an angle of 45 degrees. This is an angle of 45 degrees coming out of the page, and so on and so forth. So the 45th parallel is this entire line. This whole thing is at 45 degrees north. And this whole line is at 45 degrees south. And the fact of the matter is we can play this game for any angle that's above the equator or below the equator. So right here, we make an angle of about 32 degrees north of the equator, which means you and I in San Diego are located at 32 degrees north latitude. We live on the 32nd parallel. These are called parallels, by the way, because all these lines of latitude are parallel to one another. Hence the name parallel. So that's how we know what our latitude is. You're either north of 0 or you're south of 0. And whatever that angle is that you make with the equator or with 0, that's what your latitude is. Other than latitude, we have, of course, longitude. Longitude is a little bit trickier. So let me draw actually two pictures for longitude. I'm going to draw this one, and in this one, here's the equator at 0 degrees. But I also want to look at the Earth from above. So let me draw another circle here, and this is going to be the North Pole. So now we're looking at the Earth from above the North Pole, looking straight down. If I were to draw an imaginary line from the North Pole all the way to the South Pole, that would be called a meridian. And in this case, the very first meridian I draw is going to be at 0 degrees. And in fact, because it's at 0 degrees, I'm going to call it the prime meridian. And every other meridian is going to be based on the prime meridian. So let me draw that same line here in the picture from looking above. So here's 0 degrees, that's the prime meridian. Now I've just divided the world into, again, two hemispheres. This is the Western Hemisphere, and this is the Eastern Hemisphere. So again, this is the west side, and this is the east side. Now, the line of longitude is now just simply going to be the angle to which you make relative to the prime meridian. So if you go 180 degrees west of the prime meridian, you find yourself here, and this angle is 180 degrees, which means you're at 180 degrees of longitude. You can't really see it in this picture because if I went 180 degrees, I'm on the back side of the Earth and I'm way over here, so this would be at 180. I can also do this going east. And again, if I go 180 degrees east, I land here at the 180 degree meridian. I'm going to call this guy the IDL, or the International Date Line. And we'll talk about why it's called the international date line in a second. But it having the term date in there is really indicative that it's going to have something to do with time. Now, if I went 90 degrees west of the prime meridian, then I would be at 90 degrees west longitude. And again, I could try to draw it here in this picture, but it's not going to come out too well. This is the better one to look at. If I go east of the prime meridian, let's say by 90 degrees, I'm now at 90 degrees east longitude. So again, all your longitude is what angle do you make with the prime meridian? Now, it's fascinating actually because the equator was easy. The equator just divides the world into two equal parts. Right in the middle, northern hemisphere, southern hemisphere, boom, the equator's at 0. But the location of the prime meridian and subsequently the international date line seems to be completely rando. Like it's random. Why is it that the prime meridian is located here? And by the way, the prime meridian cuts directly through Greenwich, London, England. Why is it important where the prime meridian is located? Well, we'll figure that question out in just a second. But that's how we have our latitude, that's how we have our longitude. So again, our longitude is going to be a bunch of these meridians. Our latitude is going to be a bunch of these parallels. And so now you can clearly see that we have created a grid, hence the geographic grid. Every place on the planet is going to have a north-south, which is a latitude, and every place on the planet is going to have an east and west, which is a longitude. San Diego, California, particularly, is located at 32 degrees north latitude, about 117 degrees west longitude. That's San Diego. Now, my question is that exactly San Diego? The fact of the matter is, I'm actually down in Chula Vista. Most of you probably are up in the San Marcos area. Do we actually share the same exact latitude of 32 degrees north? Well, the answer to that question is no, we don't. In fact, we don't at all. If we look on the map, here's something that you need to know. For every 1 degree, and let's talk about at the equator or near the equator for reasons that we'll figure out later. But every 1 degree is tantamount to about 69 statute miles. Let's say, for example, you're in a boat and you're doing some form of navigation and you're told, go over there to 32 degrees and hit that port. Okay, but what if you're off by just a little bit and you're not at 32 degrees, but all of a sudden you're at 31 degrees? That's not good because you're going to be 69 miles off of your destination. You can imagine that in seafaring navigation days, especially, being 69 miles off is not good. Even in today's standards, if you're flying on an airplane from here and you're going overseas to like London Heathrow and you program the computer in the airplane, and if that program is 1 degree off, which doesn't sound like much, I guarantee you're not landing in London Heathrow Airport. So with this in mind, we actually break down degrees into something finer and finer and finer. So let's say, for example, that this is 1 degree. Latitude or longitude, it doesn't matter. So this 1 degree, again, is 69 miles. But we can break down this 1 degree into 60 equal parts. So let's do that. Let's make these 60 equal parts. So that means that 1 degree is going to equal 60 arc minutes because each one of these little parts is going to be 1 arc minute. And so let's do this. Let's just write it out. 1 arc minute. So 60 of these arc minutes makes 1 degree, and 1 degree equals 69 miles. So now if we say, okay, 1 arc minute equals 1 degree equals 69 miles, then we know that 1 arc minute equals 69 divided by 60, or 1.15 nautical miles. So a nautical mile is actually just 1 arc minute. So now if you see something like 32 degrees, 5 arc minutes, you're only going to be at most 1.15 nautical miles off if you're off by an arc minute. But the fact of the matter is, we can make this even better. If I take 1 arc minute, keep using the wrong notation. If I take 1 arc minute and I convert that or break that up in 60 equal parts, and each one of these parts equals an arc second, then I know that for every 60 arc minutes that equals, I know that for every 1 arc minute that equals 60 arc seconds. So I can actually take 1.15 nautical miles, divide it by 60, I'm going to get approximately like 0.2 nautical miles if I do that math. So that means if I say San Diego is at 32 degrees, 5 arc minutes, 10 arc seconds, and I'm only off by an arc second, now I'm only off by like 0.2 nautical miles. So you can see I'm getting finer and finer and finer detail. So if I'm in Chula Vista, California, I'm not going to be exactly the same as San Marcos. We're both going to start at 32, but these other numbers are going to be a little bit different. So now we have a little bit more finer of distance when we're talking about navigation, if we can break it down all the way to arc minutes and arc seconds. So that's important to note. Okay. This now segues to the next question. How do we determine where your latitude is located? So I've got a little diagram here. All we need to do to determine your location, latitude-wise, is by looking for the North Star or Polaris. In this case, the North Star is located above North Geographic Pole. And that star today happens to be a star called Polaris, which is the North Star. Now, I use the term today, and I use that for a reason, because the fact of the matter is, Polaris is not always Polaris. But let me rephrase that. Polaris is always Polaris, but Polaris is not always the North Star. And as a matter of fact, about 2,000 years ago, the North Star was Vega. We'll figure out why that's the case later in the class, but for right now, just know that the North Celestial Pole Star, the star that resides above North Geographic Pole, is Polaris. Contrary to popular belief, it is not the brightest star in the sky, but I'll show you in just a second how you can find Polaris. Now the question becomes, how is Polaris used to determine your latitude? Well, here's a nice schematic diagram here. Let's say that you're here in San Diego, California at roughly 32 degrees north latitude. And let's say that we make an angle, or excuse me, let's say that we make a line. And the line is just going to be drawn to our north horizon. So again, just imagine that you go outside, you look north, and you just look out toward the horizon. If you then look up and you see Polaris, the angle that Polaris makes with your north horizon, that is what your latitude is going to be. Let's say that you were standing here on the North Pole. Polaris is going to be directly above your head. Here's the north horizon. The angle that the horizon makes with Polaris is 90 degrees. You know that you are located at 90 degrees north latitude. Let's say that you were standing here. And let's say that we drew again our horizon line, and this angle from your horizon line to Polaris was 45 degrees. That would put you at 45 degrees north latitude. So that's how you find your latitude. It's simply by finding Polaris. Now we can use Polaris as our star because remember, the Earth is rotating on its axis in a nice easterly fashion or counterclockwise. That means all the stars appear to rise in the east and set in the west because the Earth is rotating on its axis. The only star that is not moving in the sky is Polaris because Polaris is on Earth's axis of rotation. So while all these stars appear to be moving in the sky during the course of the night, the only one that's not is Polaris is holding true. So that's why we can use it as our point of reference. Okay, but now here's my question. Let's say that you are below the equator. Here's your horizon line. Can you use Polaris as your guiding star? And the answer is no, you can't, because Polaris is below the horizon. You can't see it. So if you live in the southern hemisphere, you need to know what the star down here is. And there's a star here in the Southern Cross, and you would use the Southern Cross to determine what your location was, at least your south latitude location. But that's how you do it. You just look for Polaris if you're in the north. Now, the question, of course, is how do you find Polaris? Well, it's actually not particularly difficult to find. You just need to know that it's not the brightest star in the sky. If you look up to the sky, and you can do this tonight if it's a clear evening, if you find the Big Dipper is a series of stars, and it looks like one huge spoon in the sky. You really can't miss it. Once you see it once, you'll never not see it, because again, it looks like a big spoon in the sky. If you follow the last star of this big spoon to the very first star that you see, that's going to be Polaris. And Polaris is the tail star to this little constellation called the Little Dipper. So here's the Big Dipper, here's the Little Dipper, and the Little Dipper just looks like a little spoon in the sky. So when you follow the last star of the spoon of the Big Dipper to the first star in the tail of the Little Dipper, you have found the North Star. Now the next question becomes, how do I know that this is 32 degrees? Well, for most people, at least me in particular, if I went outside and if I made a fist, and if I started counting the number of fists from my horizon going straight up to my zenith point directly overhead, it would actually take me 9 fists to do it. Therefore, I know that for me, every fist is about 10 degrees. So if I go outside tonight and if I find Polaris, it's going to be about 3 knuckles worth or 3 fists worth of hand above my horizon. So I can tell immediately that it's about 30 degrees north latitude. Okay? That's how you find your latitude. Relatively easy, not particularly challenging. It is what it is. If everything was that great, that would be cool. We can find latitude, but now the challenge is, how do you find longitude? That's different. Before we get into figuring out what your longitude is, what we need to do is talk about time zones. Time zones are super important. So very quickly, let's do this. Let's say we're at 120 degrees of west longitude, very close to San Diego. We're in California. Let's say our counterpart in New York, they're at 74 degrees west longitude. If it's noon in California at 1:20, what time is it in New York? That's my first question. I'm going to give you the answer, and then we'll figure out how we got the answer. The time difference between California and New York is 3 hours. So if it's noon in California, then it's going to be about 3 p.m. in New York. There's a 3-hour difference. The question is, why? How do we know this? What the hell's going on? So let's answer that question. Let's take a look here. Let's say that you're at the prime meridian. And remember, the prime meridian is at 0 degrees. We know that the Earth is rotating on its axis in a counterclockwise direction, which means everything appears to rise in the east and set in the west. So let's say that we are here in the west. If we look to the east of us toward the prime meridian in this example, and let's say that it's noon for this person who's living on the prime meridian, you can easily see that because the sun appears to move this way, it's before noon for us. Like it hasn't gotten to noon yet. The sun is still in the eastern sky. So remember, everything is rising in the east and setting in the west. So here in the eastern sky, the sun is there before it gets to us. Now let's say that we were looking at somebody here east of the prime meridian. It's already been noon for them. That sun used to be here, but again, because of Earth's rotation, it appears that the sun has moved to the east. So for this person in the east, it's actually afternoon. And you can see because it used to be noon, but now the sun is over here. So now it's afternoon for this person. And for this person in the west, it's before noon. So if we go back to the California, New York example, California is here, New York is here, and because New York is east of us, they're always going to be ahead in time relative to us. So as a matter of fact, let's take a look at this one more time. And let's make a little diagram to make this a little bit easier. I'm going to flatten out the world and I'm going to look at it this way. I'm going to draw the picture, and in this picture, I'm going to draw the prime meridian at 0 degrees. I'm going to say that this is the Western Hemisphere, and I'm going to say that this is the Eastern Hemisphere. We've already established that because the Earth is rotating on its axis, everything appears to rise in the east and set in the west. That means Eastern, if you're east of the prime meridian, it's ahead of time. If you're west, it's behind in time. But what's important to note is this isn't just relative to the prime meridian. If you're here, anywhere east of you is ahead in time. If you're here, anywhere west of you is behind in time, because again, everything rises in the east and sets in the west. The Earth's rotation, by the way, is one complete 360-degree rotation in the time span of 24 hours. 360 divided by 24 is 15 degrees per hour. That means that the Earth is rotating on its axis 15 degrees every single hour. And if there are 24 time zones on the planet, that means each time zone is separated by 15 degrees of longitude. So, here in California, we assume we're at 120 degrees west. We have our counterparts in New York, which is at around 74 degrees west. We're both in the Western Hemisphere. But we also know that it's noon here in California, and we want to know what time it is here in New York. Well, all we have to do is figure out the difference in latitude, or excuse me, the difference in longitude between Cali and New York, and then divide it by 15. And that'll tell us how many time zones of separation there are. So 120 minus 74 is approximately 45 degrees. And if we divide 15 into 45, that gives us 3 hours. That means New York is 3 hours ahead of us in California. So again, if it's noon for us, it's going to be 3 p.m. for our counterparts in New York. That's time zones. Pretty simple. Everything's divisible by 15. I'm going to do another example problem for you in a second. But before I do, I want you to recognize something. I am using time and distance interchangeably. I am saying that New York is 3 hours ahead of us. I'm also saying New York is 45 degrees east of us. So time and longitude seem to go together. Keep that in mind because that's how we're going to inevitably determine our longitude is with time. But what I want to do is take a look at another question here. So again, this is time zone. Let's just do another time zone problem, then we'll figure out solving for longitude. Here's the question. It's 5 p.m. Friday in San Diego, California. What time and day is it in Sydney, Australia? So I'm going to draw this picture again. Oop. And here's the prime meridian at 0. We know that this is the west side, and here's the east side. We're going to put San Diego here at approximately 118 degrees. You know, we're going to use easier math. We'll just say 120. So we're going to say that we're at 120 west. So this is San Diego, SD. And Sydney, Australia is actually way over here. We'll just approximate it at 150. So Sydney is at 150 degrees east longitude, way over here. We're assuming that it's 5 p.m. Friday here in San Diego, and we want to know what time and day it is in Sydney, Australia at 150. We know that if we go this direction, then we're moving ahead in time. And we know if we go in this direction, we're going behind in time. So let's do this both ways. It's 5 p.m. We want to go all the way this way to Sydney. The question is, how many degrees of separation are there? Well, we've got 120 degrees from San Diego to the prime meridian. So this is 120 degrees. We have 150 degrees from the prime meridian to Sydney. So this is another 150. So 120 plus 150 equals 270 degrees of separation. Now we know that for every 15 degrees of longitude, that's 1 hour. So 15 into 270. So 15 goes into 27, 1. I'm going to use my longhand. 7 minus 5 is 2. 1, 2, 0. So 15 goes into 120 8 times. So that means there are 18 hours of difference between us and our friends in Sydney, Australia. So let's do it. Let's count. 5 p.m., 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've lost count though. I don't know if it's 11 a.m. or 11 p.m. Let's say it's 11 a.m. I'm going to guess. And clearly we crossed over from Friday to Saturday. I mean, we had to have. So let's assume that it's 11 a.m. Saturday in Sydney, Australia. There's got to be an easier way. And there is. We can count backwards. We don't have to count forward. Remember, we live on a sphere. So it doesn't matter if we count forward or if we go behind us and count backward. The fact of the matter is, if we go this way, we can go from 120 to 180, and that's going to be 60 degrees. And then if we go from 180 to 150, that's another 30 degrees. We're just going backwards. So now it's 60 plus 30. We have 90 degrees of separation if we go toward the west versus 270 degrees of separation if we went toward the east. So 15 into 90, 15 times 6. That would be 6 hours. So now I can just count backwards 6 hours. So 5, 4, 3, 2, 1, 12, 11. It's definitely 11 a.m. But how do I know that it's Saturday? Well, now we get to use the rules of the international date line. So remember, this is why it's called the date line. So here's the international date line. It's located at 180 degrees of longitude. If you cross over the international date line from the Western Hemisphere and you go into the Eastern Hemisphere, you lose a day. So here it is. If you cross the IDL from the Western to the Eastern Hemisphere, you lose a day. We just went from Friday to Saturday. We went from the front of the line of the Earth's rotation to the back of the line. So we've lost the day. Now, on the other hand, if you flew from Sydney and you went from the Eastern Hemisphere to the Western Hemisphere, so you cross the international date line from the east to the west, you're going to gain a day. You're going to go from Saturday back to Friday. You can't keep crossing the IDL and live forever, but if you travel overseas once, you're going to lose time, but when you come back on the way home, you're going to get some of that time back. But that's the international date line, and that's how you do time zones, though. It's completely related to the 15-degree rule. But before you get super comfortable with that, let me, of course, show you this picture of world time zones. Now, these time zones are all separated by 15 degrees. Here's us in San Diego at about 1:20, and again, we are 8 hours behind Greenwich Mean Time, or 0 degrees. But take a super close look. We're not seeing the 15-degree rule everywhere. As a matter of fact, if you went to China, it's one big time zone of +8. That doesn't make any sense because China should be 1, 2, 3, 4, 5 time zones, but it's not. And then if you take a look at other places like South Africa, going all the way to East Africa, that's all one time zone too, but that doesn't make any sense either. And then you can break this down even further. Iran is 3.5 hours. Afghanistan, 4.5. India, 5.5. Nepal, 5 hours and 45 minutes. None of it seems to make sense. The simple answer is this is politics for you. This is a political world time zone map. It's not a solar world time zone map. The solar map is going to be exclusively based on the 15-degree rule. The political map gets a little bit quirky. For us and our purposes, whenever I ask you to solve a time zone problem, it's going to be using the 15-degree rule. Okay? Anybody have any questions on this stuff at all? All right. I want to do one more thing before we actually take a little break. And that one more thing is trying to solve what's called the longitude problem. So let me give you an example. And we're not going to look at California and New York again. We're going to look at something completely upside down, completely random. Let's say that for our final exam in this class, what I'm going to do is put everybody in a big airplane. I'm going to fly us to some unknown location. I'm going to push you out of the plane. You'll have a parachute. It'll be completely safe. You'll land on the ground, and I'm going to ask you to find your way home. I'm only going to give you a sextant, and the sextant is a device where you can measure your angle relative to the stars, and so you can find your latitude. And I'm going to give you a clock. And the clock is going to be set to San Diego time. That's what you know. If you make it back, you're going to get an A. If you don't make it back and we have to send out the search party, that's a problem and you're not going to pass. So that's the key. So how do we do this? Well, let's put this into an example. We'll use that same exact one. Let's not worry about latitude. We figure out our latitude using the sextant. We find Polaris, blah, 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 no problem. But let's say that we drop off at some unknown location. So here's the unknown. We don't know where we are. So I'm going to put a line here, and here is going to be west. This direction is going to be east. We just simply don't know where we're at. You only have a watch on you, but good for you that the clock is set to San Diego time, which you know is about 120 degrees west longitude. You don't have any other clock. There's nobody around you who's going to be able to tell you the time. But what you can do is figure out when it's solar noon for you. Because when it's solar noon, the sun is at its highest point in the sky. Not necessarily directly overhead. Remember, that's not always going to be the case. But it's at the highest point in the sky at solar noon, which means that the shadow is going to be the shortest. So let's say for sake of argument, you're at this unknown location for a couple of days, and you determine when it's solar noon because you determine when the shadow is the shortest. So now let's say for sake of argument, you know when it is noon or solar noon at the unknown location. And at the same exact time, you look at your watch. And your watch is again set to San Diego time, which you know is 120 degrees west longitude. So let's say at this time, when it's solar noon at your unknown location, at 120 degrees west longitude, at this same time, it's 5 p.m. Okay, it's noon for you at the unknown, it's 5 p.m. in San Diego. You can figure out where your unknown location is now. So again, San Diego, here's going east, here's going west. East is ahead in time, west is behind in time. If it's 5 p.m. for you, and then noon is where the unknown location is, the question you ask yourself is noon behind or ahead of 5 p.m.? In this case, it's behind. Noon is over here. 5 p.m., noon hasn't hit yet, right? So for you, in your unknown location, you're behind 5 p.m. If that's the case, then the difference of hours is 5 hours. So 120 is here. You are now 5 hours west of 120. So every hour is 15 degrees. So that's 25 or 75 degrees. That puts you at 75 degrees west of 120 west. So where would that put you? Well, 120 goes to 180. And that's 60 degrees. And you've got 15 more degrees to go. So if you're at 180 and you got to go 15 more degrees, then 15 minus 180 is 18, 17, 10, 5, 65. That means that your unknown location is at 165 degrees east longitude. Okay, that's how you do it. Now, you're looking at this going, okay, well, it's a little bit squirrely, but I think I sort of get it. There's a relationship between time and longitude. And there is. That's how you find your longitude. You need to know what time it is at your new location. You need to know what time it is at your old location at the same time. That'll give you the time zone difference. And once you know the time zone difference, using the 15-degree rule, you can figure out what your new longitude is. So all you need is a couple good clocks, right? Okay, here's the problem. If we go back hundreds of years and we ask ourselves, well, what kind of clocks do we have? We have sundials and we have pendulum clocks. But let's say that we really need navigation and we're navigating at sea because it's a seafaring age. The world is exploring itself by boat. And if you've wondered why the prime meridian is located in Greenwich, London, England, it's because Greenwich, London, England had the strongest marines back then hundreds of years ago. The United Kingdom was it. Everybody wanted the prime meridian because the prime meridian is the start of time, right? For trade purposes, knowing what time it is really important. Everybody wanted the prime meridian. Greenwich, London, England has it. But how do we figure out time? You can't do it. You can figure out your time in London, England, but once you're on a boat, how do you figure out time? It's nearly impossible because you've got pendulum clocks, and I guarantee you pendulum clocks don't work particularly well out at sea when the boats are yawing back and forth. So in fact, in the early days of shipping, they would do what's called running the latitude. They would figure out their latitude and then just like go due east or due west and hope for the best. But a lot of ships were actually lost at sea because they couldn't figure out their longitude. So a very large contest was created by the British monarchy. And the contest was, can somebody build us a clock that could work at sea? And as a matter of fact, it was a very large competition, and the winner of the competition was a gentleman by the name of John Harrison, who was a carpenter by trade, but he started to create chronometers that would work at sea. As a matter of fact, this is Harrison's Sea Watch number 1 with a winding crank. This thing is 5.2 inches in diameter, so it's pretty big. Took him about 6 years to design and make, and it's accurate to about 1 arc minute, which we know what an arc minute is. It's about 1.15 nautical miles going from Portsmouth, UK to Kingston, Jamaica, which is a 6-hour time difference, 81-day voyage, accurate to about 3 seconds per day. That's not bad. You look here at the Sea Watch H5, tested in 1772 AD, also 5 inches in diameter. Now this one accurate to 0.33 seconds per day. So the fact of the matter is, this longitude problem was the precursor to us actually having modern clocks and modern day watches. This solved the problem because it figured how to determine your longitude, especially out at sea. Now, you can go to Greenwich, London, England, and you can go to the museum there. And here in the museum, you can see, here in the museum, there's the prime meridian. You can straddle both sides of the eastern and western hemisphere if you want. And the prime meridian goes right through the museum. You can go inside the museum and you can see John Harrison's clock. It's a pretty cool place to be. Okay, we went through latitude, we went through longitude. We know what the shape of the earth is and the size of the earth. We also figured out how we determine our latitude, how we determine our longitude. We know something a little bit about time zone, and we know a little bit about the international dateline as well.